First talk of this afternoon, we'll have Ranjan from Julia Computing, and he'll be talking about Circuitscape, a package for landscape ecology.
So, good afternoon, everybody. My name is Ranjan, and I am going to talk to you about this package called Circuitscape. So, when I was thinking about titling this talk, I was caught in two minds, because this talk is actually two talks. So the first part of the talk, the first aspect of it, because I'll be going back and forth, is talking about what Circuitscape actually is. What is the actual work that I did, and how people are using Circuitscape. But the other thing I want to touch upon, and I think this is very important from a Julia perspective, is how do you write an end-to-end application in Julia? So you have this great Julia package that outperforms everything else in other software ecosystems. And what you want to do is you want to get it out to people. You want to package it and ship it, and allow people to install it on their computers with as little hassle as possible, and start using it straight away. And of course, if the other person is already using Julia, he could add the package. But what if he doesn't want to install Julia, as does happen in a lot of enterprise situations? And I'm sort of going to spend fair amount juggling between both of these two topics. But first, I want to tell you what exactly Circuitscape is. So Circuitscape is a tool for landscape ecology. It borrows algorithms from electronic circuit theory to measure connectivity in the landscape. So if you have this diverse landscape with rivers and hills and roads, natural barriers like hills and mountain ranges, and man-made barriers like roads, highways, and railway lines. Circuitscape sort of lets you analyze how animals would navigate and move in that diverse, complex landscape. It's mostly based upon the work of these two papers, Isolation by Resistance, which sort of talks about how circuit theory, what circuit theory is, and how it can be applied to study animal movement. And broadly speaking, and the second paper, using circuit theory to model connectivity in ecology, evolution, conservation, and how the theory connects to most of the applications that people, or the questions that people are asking about animal movement, and what are the right ways to think about conservation policies based on simulations coming from Circuitscape. So just to briefly illustrate the concept, consider the landscape on the left over here, and look at these two green patches. So these two green patches are what we call protected areas. So protected areas are places where animals can move freely. It's like the jungle, and from there, just look at figure number 2. Well, it's supposed to be a line here, but anyway, just imagine that there was a path that the animal followed from this protected area over here to this protected area over here. So what Circuitscape allows you to do is to sort of think about all the various paths, or sort of simulate all the various paths that animals can take from this protected area here all the way down here. And so one possible way to think about that is, hey, why can't the animal move along the quote-unquote least cost path, right? But Circuitscape, in some sense, simulates all the various paths that animals use, and allow you to observe how, on average, how animals can move across the landscape. So these concepts are better illustrated with some examples. So Circuitscape is used in, let's say, wildlife corridor design. So if you have this heterogeneous landscape, and you find that there are places where animals are places where the flow of animals is constricted, where there are a lot of barriers around that particular path, and there is this critical path that the animal has to flow along, what people tend to do is they tend to buy that particular part of land, create something called a wildlife corridor, which a lot of conservation organizations tend to do. So if you look at the example over here, you would see that these yellow patches over here are where the animals are very highly concentrated, so you could call these points of restricted flow, and those are the candidate places where conservation organizations should sort of look towards buying land and promoting conservation policy. So again, similar application, landscape genetics, how the properties of the landscape affect gene flow and genetic differentiation amongst the populations in the landscape. Movement ecology, which I just got into. And a new, more interesting thing that people are doing now is connectivity for climate change. Now, since, with the advent of climate change, many species will have to move in some direction to account for climate change, because the habitat that they're used to is changing, and many ways than one. To encounter a similar habitat, they have to move either upslope or northward. And while they do that, they tend to encounter barriers like roads, agricultural areas, and cities. And so this is how you'd see all these newspaper clippings of animals moving through cities and villages, and panic as a result of that. So in order to maintain this connectivity with one candidate protected area to another candidate area which has a similar climate, having accounted for climate change, ecologists find that they have to maintain population connectivity. So let me quickly go into some real examples. So this was a study done in 2015 in India, where they took a part of central India and they tried to find the points of restricted flow for the Indian tiger. So this was the part that they were looking at. And this is India, and you'd see this little part in central India that this was the area of study. And what they did was they ran Circuitscape, and then as before, look at the green patches over here. The slightly dark green patches represent the protected areas. And these highly concentrated yellow bits represent the points of restricted flow, and we call these pinch points. So I'm probably going to call these pinch points from henceforth. So people look at these pinch points and see, are there any natural man-made barriers that go across these pinch points? So if you look at the key, some of these all these white regions here represent road and railways, and these tend to cause problems for animals. So animals either get killed or encounter humans die. All sorts of problems can be averted when these pinch points are considered as candidates for wildlife corridors. Another quick example I want to show you for connectivity in climate change. So this is a map that was, let me just open this in a new tab. Yeah. So this was a map that was generated based on a study by Professor Joshua Lawler, who's a professor at the University of Washington. So what these parts are, let me see if I can try and zoom this a little. Yeah. So this, of course, is North America. So if you look a little closely at this graph, what this is simulating is the average path that amphibians or birds or mammals are moving across the landscape under climate change. So these are of course these are done at a very coarse resolution, so there's a lot of averaging done. But on average, these are the paths that all these different classes of animals are taking through the landscape. So you can see all this flow is like generally directed northward towards cooler climates, and there are some regions where you might find that there are mountain ranges where animals tend to go upslope. So of course they conducted this study throughout North America, so you could observe a similar phenomenon in South America, and for some reason all these animals seem to be going towards Ecuador. So this is it's called, let me see what this thing is called. It's called, so this amazing map is called Migrations in Motion. So you can go to tnc.org/migrations in motion, and you should be able to get a nice little guided tour as to how these things.
Maybe just to be accurate, these are not happening at this moment. These are expected to happen with every additional degree of warming.
Yes, that is true. To be precise, this isn't happening at the moment, but this is expected to happen as as climate warms more and more with every degree. So just quickly moving on. The last application I want to quickly glance over is you can Circuitscape is also used. Switching gears a little bit, Circuitscape is also used to predict the spread of wildfire. So this is a map that shows the susceptibility of the various parts of landscape. This is the Sonoran Desert in Arizona. So the red regions mean that there's a higher probability of fire starting there, and the green regions mean there's a lower part. And this is sort of fed into Circuitscape, and the landscape is analyzed to produce a map where the connectivity in the landscape is sort of used to determine how and where the wildfire will flow. This is again excellent work done by Miranda Gray, one of my collaborators, and so one interesting bit to note about this is that there are parts in the landscape, even though they don't have a very high probability of catching fire themselves, by virtue of their landscape connectivity, they can actually catch fire. So this sort of gives you an average picture of the large fire probability in this entire landscape. So moving on, so I just want to quickly talk about the package itself. So what the package does is that it creates this large grid on the landscape. It sort of abstracts the entire landscape as a large grid. Takes satellite data, divides it into a raster grid cell, and each grid value represents a resistance to animal movement. So what is the impedance that this particular the landscape provides to this particular animal? And what we do is that we construct this large graph, large sparse graph from this raster grid of the landscape, and we sort of take two candidate points, maybe across two ends of the landscape. This again depends on what the ecologist wants, and we sort of inject current at one particular node and sink current through the other. So this generally involves solving a large system of linear equations, and so the system that comes up are called Laplacian systems. They are called Laplacian systems, and by default we solve it with an iterative method, conjugate gradient with a algebraic multigrid preconditioner, and this was also implemented as part of the project. It lives in algebraic multigrid.jl. Or if we have slightly smaller graphs, we can just use a direct Cholesky decomposition, which we get via the Cholmod thing that comes in base Julia. So after doing this solve, it sort of writes current maps. So what it's trying to say is, you have this large landscape with all these grid cells. How much current is likely to be in each of these landscapes? So it sort of calculates the current in each of these grid cells, and this sort of represents higher current there sort of represents a higher probability of animal movement. So a good way of thinking about it. So this package was originally written in Python by Brad McRae and Viral Shah and Tanmay Mohapatra. Viral and Tanmay are both part of the Julia community, and now we sort of rewrote this entire package along with the solvers, everything in Julia. In fact, every single piece of software I'm going to talk to you about that's part of this work is all in pure Julia. So as we rewrote in Julia, we got some pretty significant benefits. It's about 8 times faster with the default solver than the Python version, and this is on solving really large problems. It's about 8 times faster, even doing the parallelization and everything. But the parallelization can happen only on Mac and Python. Sorry, on Mac and Linux in the Python version. So there exists no you can't do parallel solves on the Windows operating system when you're using the Python package. So when we use Julia, Julia is naturally parallel on on all operating systems. And this 8x speed up usually gets far more significant as and when people use large Windows machines. And most of our user base happens to be in Windows. So even though I say 8x to be, it's mostly an estimate on the conservative side, and most people tend to see far more speed up as they use their large Windows machines and take advantage of the parallel computing. We also have, since I've written completely generic Julia code, you can also perform single precision computations as opposed to the default double precision computations, and you sort of trade off performance and accuracy, something that you just can't do with the Python package. So this just gives you a general idea. Okay, so the blue bar over here is Python. And this of course is time taken, and this is size. So this is the order of increasing size, and this is the order of increasing time. So you can see this blue graph actually getting bigger and bigger, way bigger with every single problem size. And from 48 million onwards, it just took too long. I stopped bothering to measure. So you can see the Julia version, which is the red bar here, with the default solver, takes much lesser, and up to 8 times lesser. And for smaller problems, the Cholesky factorization solver seems to work very well, and it's even faster than our normal Julia iterative solver. But more than this benchmark chart, I kind of want to show you the feedback from the users itself. So we presented this work just a few days ago at the North American Conference for Conservation Biology in Toronto, and we met users there who told us pretty encouraging things. These people usually have simulations that take in the order of weeks and days, and we managed to reduce it fairly significantly in Julia. So with the default solver, she managed to get about 35 hours, and this is a fairly limited desktop PC she was using, and an order of magnitude, like less than a day for the same problem that took 8 days to run. So her original problem took about 8 days to run, and the Julia problem took a little more than a day with the default solver, and with the Cholmod solver took less than 24 hours, which is which helped. Sorry.
I should point out that this is without parallelism, right?
This one, let me see. No, I think she did use parallelism on this. She did use parallelism on Windows on this. But this kind of problem had no parallelism. So we have another case where the problem in the Python version took about 36 minutes, but in the Julia version it took less than 3 minutes. So we see these kinds of things all the time as well. And even at the conference, we encountered users with really large problems for which their Python package crashed, and we managed to solve them in the Julia version. So this one went to about 437 million nodes, and the Julia version was able to run at about 3.5 hours, while the Python version just crashed. So yes, the fair amount of improvements in the package itself. But just switching gears at this point, this is usually the case for most people. A lot of people take their projects and they shift it to Julia, and they find that they get good results. But they now need to convince their colleagues or convince somebody else to use it. So usually, with a Julia package, it's usually something like this. You just do using Circuitscape, and then you just compute and you get a bunch of numbers. But what you want other people to do is to sort of pick up and use your package and have it really easy to install. So you want to move from package to full-fledged application. And we have this working on Circuitscape right now, and I want to go take some time and go into how we managed to do that. So as I was saying, I have a great Julia package. Now what? All the work I'm about to present to you is all done completely end-to-end in Julia. So from the solvers, an algebraic multigrid.jl, the package by itself with all the parallelism and everything, and these two parts I'm going to cover now, the UI and the packaging and shipping. So the UI again is in completely pure Julia code, and the packaging is all completely in Julia as well. So step one, you need to build a UI. And now, if you're like me, if you're a numerical computing person, you're like, well, how do I build a UI? I don't know any JavaScript. So there are a few decisions, that you need to sort of think about. First is what kind of platform. Ideally, you would like to choose a platform on which, your users, irrespective of which platform they're on, they'll be able to use your software. So I chose Electron, and we have a great Julia package that interfaces to it called Blink. So the advantage of Electron is that it works on all three platforms, and it's great. And one important thing is it, as opposed to a web app, it can access your file system. So you can point your Electron app to various things that are happening, the various things on your computer, and you can just run your simulation on that. But the advantage is that it can hang up system resources. So to build a GUI, you would need Interact. I use this Interact Balmer ecosystem with CSS Util and WebIO. It's all Shashi's work, and it's very sort of easy to get it to work. And I just wrote up a simple UI in a few lines of Julia code, using the ecosystem, you can sort of have the Julia code. Whoops, this one is not responding. But anyway, via using observables, you should be able to extract the data from your UI as well. So that's one thing. And then if you want to style your text, there's another great package called Tachyons, which sort of wraps over the Tachyon CSS utilities and gives you some interesting templates that you can use by default. And this is then very quickly going into packaging and shipping. Yeah. So in packaging and shipping, now that you have a great UI, how exactly do you ship it to users? And a lot of people might have heard of package-compiler.jl, but there's this new package that we've been working on called application-builder.jl that just needs two scripts. One that you sort of define as your default application behavior, and a script that sort of specifies your dependencies. And then you just call this function called build app bundle, and it'll just work. So I'm not going into the details of how it's worked because I'm running out of time. So for that, please refer to Nathan Daly's talk on Thursday. It's a great talk, and he goes into the mechanics of how this all works. But what I'm going to do is quickly show you how it actually works, in practice. So I don't have Julia installed on this system. Okay, so this is a simple Azure VM that I spun up. I don't have Julia installed on the system, but I just installed this binary. I just downloaded this binary, and I'm just going to show you how it looks. Of course, it's a standard installer as you'd expect. And on Windows, Application Builder gives you this installer by default, so you step through the licensing. Let's see if I can, step through the license, you agree with the license, you figure out where you want to install it, and then it just installs. It'll take a couple of minutes to install, and then after that, optionally you can create a desktop shortcut, which you can access pretty easily. Oops, okay, so it looks like it's taking, so what this is doing is essentially bundling everything together, and then after that, you get this little terminal over here that comes by default with Electron on Windows. So I've used this mostly for some debugging, and if I don't know whether you can see all that. So all these things just say that all the dependencies are right on that particular system only, within that particular bundle. So you can see all this entire UI, along with buttons, the form, logging, all written in Julia and all packaged in Julia. Yes, they'll take a little while, so we'll just run them and come back to them. So, oops, sorry. Just going to go quickly again. So we made a number of contributions to the ecosystem via this project. One to linear algebra, in the form of algebraic multigrid.jl. And thanks Viral and Sasha for all your help in developing that package. And we have a future plan with regard to this experiment mode with more solvers in Circuitscape. Introduce parallelism in the software via using Q arrays, and the contribution to Ecology is the package itself. And I need to thank Brad McRae, the late Brad McRae, who came up with all the foundational ideas for the software. We have a bunch of plans on parallelizing and improving the software itself, along with performing additional complex tasks like forcing the current to run in all the various parts of the landscape and everything. So that's how this would sort of look like. You sort of divide it into different climate zones for animals. And again, very quickly thanking people. So with the GUIs, thanks Shashi and Pietro for your help, and thank you Nathan Daly for the application builder stuff, and Simon Danish and Jameson Nash for the static compilation. Yes, TLDR, Julia has a full development stack if you want to build applications end to end, and Circuitscape is a widely used tool in landscape ecology, and the Julia version is much better than the previous versions. Thank you very much.
Thank you for your talk. Does anyone have any questions? Lots of yes.
I see that it's also a Julia package, the circuitscape.jl.
Yes.
So what's the relationship, or what's the difference between using the binary version that you've packaged or using the version through the Julia REPL?
There's no real difference. It's essentially the same. I mean, like it's the same thing. I've just run it through package compiler, produced that binary, and shipped it to you.
Most of the users of the tool have no idea about programming. They just want to click, load a file, and run.
Yes.
If you're even not the Julia word, they'll run on it.
Yeah, and many companies have problems with installing new software. Have to get it approved and all that. But
Sure. Yeah, I understand that. I was thinking I might use it.
Oh yeah, we're looking forward to it. Yeah.
So great talk. And we're really interested in the PDE area about solving Laplacian systems as well, of course. And I really like what you've done with algebraic multigrid.jl. But I'm kind of wondering, you've been kind of going down this road to parallelism, right? And I saw that you're working on multi-threading, but I was wondering if you were looking at doing any distributed parallelism with your preconditioners.
Yes,
okay.
yes. I'm sort of thinking about, we've heard of Boomer AMG and problems like those that sort of distributes the preconditioner amongst various nodes, and then after that starts the computation. So that's the plan going forward, and trying to come up with that kind of distributed system.
Actually, it's worth saying that there is
Yes.
there is an addition. There is a different version of Circuitscape that extends the Python code to use Boomer AMG.
Yes.
For Gflow, they published it, but it can only be used on the one machine.
Yeah, it's.
Any other questions? Okay, we have time for one more.
Just one about the ecology side of things. Animals also need territory, but if it's an inter-circuit simulation, you can have this infinite animal density in Ecuador. Is this realistic? I would have expected more sort of hydrodynamic code where animals are not arbitrarily compressible.
So full confession, I have zero ecology experience. I have no background ecology. I just worked on the numerical stuff involved. But I can point you to the relevant papers, and I can set up communication and stuff like that with the with the conceptual side.
On what this achieves and what it does not, and it's a modeling tool, so there's always room for bringing in new things.
So it's just one abstraction of animal movement, because there are other abstractions involving least cost paths and stuff like that, where they assume animals have perfect knowledge of the landscape. But here we assume that animals have no knowledge of the landscape. So when they have knowledge, they think about stuff like territory. And so it's usually like somewhere in between where the truth lies. And that's what people studying these cases tend to do, use a blend of methods.
But interesting is that one area in
It is? Oh, huh. That's great. Awesome.
Okay, if we could all thank the speaker again.
Yes, thank you.